The Great Pyramid's base is almost a perfect square, aligned to true north with astonishing accuracy. How did ancient builders accomplish this without computers or laser guides? By the end of this video, you will know the exact tools and methods that made such architectural perfection possible. We will uncover how a simple weight on a string could define a vertical line for a colossal wall, and how a knotted rope was used to create a perfect right angle. These forgotten instruments reveal a story of human ingenuity that rivals our modern technology. What forgotten innovation from the ancient world do you believe was the most crucial for shaping our history? That quest for perfection began not with stone, but with a simple, universal standard. To build something that would last for millennia, the ancient Egyptians first had to answer a fundamental question. How do you ensure that every single person working on a project, from the chief architect to the laborer hauling blocks, is using the exact same measurement? Their solution was both elegantly simple and profoundly effective. They turned to the human body itself. The royal cubit was the master key to their entire architectural system. This unit of length was defined as the distance from a man's elbow to the tip of his outstretched middle finger. But this was no rough estimate. To prevent variation, master craftsmen created official cubit rods from durable materials like granite or precious woods. These rods were the absolute standard, the literal rule by which the pyramids were measured. Think of them as the ancient equivalent of the modern meter, a physical object that defined a unit for an entire civilization. On a bustling construction site, the master builder would have used his official rod to create many working copies. These could be simple, carefully marked lengths of wood or even knotted ropes, distributed to teams across the vast project. This ensured that a cubit measured at the north corner of the foundation was identical to a cubit measured at the south. This meticulous standardization was the invisible framework upon which the visible miracle was built. It transformed a grand vision from a pharaoh's mind into a set of numbers that could be communicated, replicated, and executed with breathtaking precision. So before a single drafting tool could be lifted, this system of measurement had to be firmly in place, a silent agreement in stone and cord that allowed thousands to work as one. With that universal system of measurement in place, the builders could now turn to the very direction of the world around them. Gravity became their silent partner in this endeavor. Imagine a simple, tear-shaped stone carefully suspended from a single flaxen thread. This is the Plumbob, a tool so fundamental that its design has remained virtually unchanged for over 4,000 years. Its purpose was absolute: to find a line that pointed directly to the Earth's core, a true vertical. An ancient architect would stand before a newly laid course of stone, holding this instrument steady. As the weight settled, the string would become a perfect, unwavering line against the wall. Any deviation, any slight bulge or inward lean would be instantly revealed. But its use went far beyond a single wall. To align a massive structure like a pyramid to the cardinal directions, builders would set up a circular enclosure of low walls. By marking where the shadow of a central pole crossed this circle throughout the day, they could trace a perfect east-west line. Then, using nothing but a set of plumbobs, they could project this line upward, creating the perfect 90-degree angles needed for the corners. Think of the confidence required to build a structure hundreds of feet high, knowing that every single block had to be checked against this simple string and weight. Craftsmen would hang multiple plumb lines down the faces of a rising pyramid, a gossamer grid against the massive stone. They would then carefully trim and adjust each new block to align with these vertical guides. The slightest error at the base would be magnified into a catastrophic lean at the summit. This relentless pursuit of the vertical was not just about aesthetics. It was about survival. A perfectly plumb wall distributes weight evenly down into the foundation, allowing a monument to withstand the relentless pressure of its own mass and the passage of millennia. This elegant dance with gravity, using one of the simplest tools ever conceived, set the stage for an even greater challenge, mastering the perfect horizontal plane. But gravity's perfect vertical was only half the battle. A structure that is perfectly upright will still collapse if its base is uneven, if the immense weight of stone above cannot find a stable, level path to the ground. To solve this, ancient builders invented a companion to the plumbob, a tool often shaped like the letter A. From the apex of this wooden frame, a plumb line would hang, its weight pointing directly downward. When the two legs of the A stood on a perfectly level surface, the dangling string would align precisely with a mark carved at the center of the horizontal crossbar. This simple alignment transformed an abstract concept into a physical reality anyone could see and verify. It was called the A-level, and it gave builders mastery over the horizontal plane. Imagine a team preparing the foundation for a Roman aqueduct, a structure that had to carry water for miles across rolling hills. Using a series of these A-levels placed end to end, they could create a continuous, unbroken level line across the landscape. Each massive block for the aqueduct's channel was then set to this perfect grade, ensuring that water would flow steadily and powerfully, pulled by nothing more than a consistent, gentle slope. Without this reliable baseline, the entire system would fail, with water pooling in low sections or rushing uncontrollably in others. Inside a Mesopotamian ziggurat, this same principle created the vast, flat ceremonial floors that felt solid and eternal underfoot. The level ensured that every single stone core sat perfectly flat upon the one below it, distributing the crushing weight evenly and eliminating points of weakness. This was not merely about creating a flat floor, it was about engineering stability that could endure for ages. The A-level provided the trusted foundation from which all other complexity could grow. Once a builder had established a perfectly level plane and a perfectly vertical line, they held the two fundamental axes of our world. With these two constants secured, they could then confidently begin to construct the geometry of the divine, laying out the perfect squares, triangles, and circles that would define their most sacred spaces. How did they then move from these straight lines to the precise angles and curves that gave ancient structures their soul? The straight line and the perfect angle, however, are just the beginning of a design. To translate a vision from the mind into a mountain of stone, ancient architects needed a way to freeze their ideas, to create a permanent guide that could be shared and followed. Long before the pencil, their tool of choice was the scribing knife, a sharp metal stylus used to carve lines directly into clay tablets or prepared wooden boards. This was not sketching. It was a deliberate act of incision, physically scoring the design into a durable surface. In ancient Mesopotamia, we find fired clay tablets bearing the detailed plans for vast temple complexes, complete with precise dimensions and annotations. These were the original blueprints. The unforgiving nature of the medium demanded absolute focus and precision from the designer. A mistake carved into wet clay was difficult to remove, forcing a clarity of thought and a commitment to every single line. This process created a tangible master plan, a portable piece of the architect's intellect. An overseer at a distant quarry could hold such a tablet, understanding exactly which stone to shape. A team leader at the foundation could reference these incised lines to verify a critical angle. This practice was the vital conceptual bridge, turning abstract calculations into a physical roadmap for thousands of workers. It captured the entire project in miniature, locking in the sacred geometry and proportions long before the first foundation stone was ever set. This shift from mental concept to physical plan set the stage for the next revolutionary leap, when these precise lines carved in miniature were scaled up to guide the shaping of stone on a monumental level. That knotted rope stretched taut in the desert sun was more than just a tool. It was the physical manifestation of a profound geometric truth. If you take a cord and tie 12 evenly spaced knots, you can create a triangle with sides of 3, 4, and 5 units. When you pull this triangle tight, the angle between the 3-unit and 4-unit sides is a perfect, unassailable 90 degrees. This is the famous 3-4-5 triangle, a principle later named for the Greek thinker Pythagoras, but understood and applied by master builders for centuries before. With this single rope, an Egyptian architect could lay out the perfectly square corners for a temple's foundation, scaling the triangle up to any size needed. It was a portable, infallible geometric proof that anyone could use, but ropes fray and stretch over time, and the demands of mass production on a building site called for something more permanent. This empirical knowledge soon became cast in wood and metal. The set square was born, a rigid L-shaped tool that provided an instant, unchanging right angle. A stonemason could now simply press this metal guide against the corner of a freshly cut block. A quick glance at the seam of light between the tool and the stone revealed any imperfection, allowing for immediate correction. This leap from a flexible rope to a fixed square was a revolution in quality control. It meant that every single block destined for a Roman fort wall or the columns of the Parthenon could be checked and standardized, ensuring that walls met with unwavering precision. The right angle became the silent, rigid skeleton upon which entire civilizations built their most enduring symbols of order and power. But geometry is not built on straight lines and corners alone. The human spirit also yearns for the curve, the circle, a shape that has no beginning and no end. How did these masters of the straight edge then turn their attention to capturing the perfect circle? The rigid right angle could frame a city, but it could not capture the heavens. For that, ancient builders turned to another tool, one that mirrored the very motion of the stars. The compass, in its most fundamental form, was nothing more than a pivot point and a scribing arm. Yet this simple device allowed them to inscribe perfect circles onto clay tablets and wooden boards, freezing the infinite loop of a circle into a workable plan. This was the key to creating the cylindrical drums of massive columns. Each stone had to be an exact circle in cross-section, so it could stack seamlessly with the one above and below, forming pillars that appeared carved from a single piece of rock. But the compass truly changed the world when its arc was lifted from the page and translated into stone, creating the arch. The majestic arcs of a Roman aqueduct are nothing but segments of a giant circle, carefully plotted with a compass and then constructed with precisely shaped voussoirs, the wedge-shaped blocks that form the arch. The genius of the arch is how it redirects weight outward and downward into its supporting piers, allowing for vast, open spaces below. This simple curved line, born from a draftsman's compass, enabled builders to span rivers and valleys with structures of incredible strength and grace. The circle was more than a shape, it was a philosophical ideal representing cycles and celestial harmony. Many temples and tombs were laid out using sacred geometry, their proportions derived from the relationships between circles. This spiritual significance fueled the pursuit of geometric perfection. Mastering the circle through the compass was the essential step toward the most ambitious of all ancient ceilings, the dome. A dome is simply an arch rotated around its central axis, a three-dimensional expression of the compass's perfect sweep. This tool unlocked curvilinear forms, pushing architecture beyond the simple stacking of blocks and into the realm of true structural engineering. It demonstrated a profound understanding that stability could be found not only in straight lines and right angles, but also in the graceful, enduring strength of the curve. That simple right angle, perfected on a single stone, was about to be projected across an empire. The Romans faced a challenge far grander in scale than any single temple or tomb. They needed to impose order onto the wilderness itself, to carve straight roads through forests and lay out entire cities from scratch. Their secret weapon was the Gromer. Picture a tall staff planted firmly in the earth, topped by a cross that could rotate. From the end of each arm of this cross, a plumbob hung on a string, creating 4 perfectly vertical lines suspended in space. A Roman surveyor, known as an agrimensor, would stand behind this instrument and look past 2 of the opposing plumb lines. By aligning them visually with a marker held by an assistant hundreds of feet away, he could establish a flawlessly straight line across the landscape. Then, by simply rotating the cross 90 degrees and repeating the process, he would create a second line perfectly perpendicular to the first. In that single point on the ground, he held the power to generate an entire grid of right angles, a geometric net he could cast over miles of territory. This was the genius of the Gromer. It scaled up the principle of the set square to an almost unimaginable degree. With it, the agrimensor could lay out the entire street plan for a new colonial town, ensuring every intersection was a perfect 90 degrees and every city block was uniform. This systematic approach, called centuriation, was also used to divide vast tracts of conquered farmland into precise, measurable squares for settlement and taxation. But perhaps the Gromer's most enduring legacy is the Roman road. Those legendary highways that stretched to the horizon in a dead straight line were not a product of guesswork. Surveyors using the Gromer would mark the route, setting a long series of straight segments and exact right-angled turns, allowing for efficient movement of armies and trade across continents. This tool transformed the very concept of space, turning chaotic nature into a measured, organized, and controllable asset. The Gromer was the culmination of ancient drafting, taking principles proven on a single building and applying them to shape the world itself. This mastery over the landscape provided the essential foundation for the next great leap, the application of these precise geometric principles to the most ambitious and iconic structures ever attempted. These drafting principles reached their ultimate expression in the Great Pyramid of Khufu. Across its 13-acre foundation, ancient engineers achieved a level of flatness that deviates by less than an inch. How was such a vast plain made so perfectly horizontal? The evidence points to a brilliantly simple system. They likely dug a grid of shallow trenches across the entire bedrock site, filling them with water. The surface of still water always finds a true level, creating a continuous, unbroken reference plane. By measuring down from this water line at countless points, workers could painstakingly trim the bedrock itself to match this perfect horizontal. This was the level scaled up to a monumental size. With the base perfectly flat, the next challenge was establishing the square. The sides are nearly a perfect square with an error of less than 0.1%. The 3-4-5 rope triangle method provides the most plausible explanation. By stretching a knotted rope into a triangle with sides of 3, 4, and 5 units, they could project a perfect right angle from a baseline, scaling this method up to define the pyramid's immense corners. Yet the pyramid's most stunning alignment is to the Earth itself. Its sides run almost perfectly north, south, east, and west, with an accuracy within a tiny fraction of a single degree. This precision likely came from a tool called the Merkhet. This instrument was a narrow, palm-sized bar with a notch cut in its center, used with a plumb line. A priest or astronomer would set up two of these devices to sight on a specific star as it crossed the meridian, the north-south line in the night sky. By tracing this celestial line onto the ground, they could establish a true north-south axis that was far more accurate than any solar method. The Great Pyramid's base is not merely a platform. It is a perfect geometric form, born from water, rope, and starlight. It stands as a powerful testament to what could be accomplished by combining simple, reliable tools with profound understanding. This foundational mastery over the flat plane, the right angle, and celestial direction set the stage for the structure's breathtaking ascent into the sky. Yet even the mighty Roman road required more than just straight lines. To sustain its sprawling cities, Rome needed a constant, reliable flow of fresh water, channeled across hills and valleys for dozens of miles. This monumental task demanded a level of precision that far surpassed the needs of a single building. The gentle slope of an aqueduct had to be perfect, a consistent decline of just a few inches every 100 feet. Too steep and the water would rush violently, eroding the channel walls. Too shallow and it would stagnate into a muddy pond. To master this immense horizontal plane, Roman engineers developed their most advanced leveling instrument, the Corobates. Imagine a wooden bench as long as a modern bus, supported by 4 sturdy legs. Along the top of this 20-foot frame ran a shallow, carefully carved groove. The principle was brilliantly simple. Engineers would fill this central channel with water. The surface of still water always finds a true level. If the water perfectly touched reference marks carved at both ends of the groove, the Corobates itself was perfectly level. On a calm day, this water line provided an exquisitely precise reference, but the Romans were practical builders who could not wait for perfect weather. For windy conditions that would ruffle the water's surface, the Corobates was equipped with a set of plumbobs hanging from each end. By ensuring these strings were aligned with marks on the legs, the engineers could verify the level without needing calm water. A team would move this massive tool across the landscape in a patient, leapfrogging procession. They would take a reading, then move the Corobates forward, using its own length as a giant measuring stick to continue the unbroken level line. This painstaking process allowed them to map an imperceptible gradient across vast distances, plotting the aqueduct's path with astonishing accuracy. The enduring legacy of the Corobates is not just in the stone arches that still stand, but in the very principle of bringing life-sustaining water across impossible geography. It represents a shift from ensuring a block was level to ensuring an entire landscape was level, a tool that could tame nature itself on an epic scale. With such mastery over the straight line and the perfect grade now achieved, the focus of architectural ambition could turn from pure engineering to something more expressive, where precision served not just stability, but also beauty and form. A single master carver would first perfect the elegant curve of a leaf or the sharp angle of a molding in a small clay model. That model then became the source for a flat, durable template, meticulously cut from sheet bronze or a hard piece of wood. This template was a stencil for stone. A worker could hold it firmly against a roughly shaped block and trace its profile with a sharp metal point, transferring the complex design in an instant. Suddenly, the most intricate pattern was reduced to a simple, repeatable task. On the site of a great Greek temple, this meant that dozens of artisans, working simultaneously on different columns, could all carve the exact same number of flutes, each one with the same depth and graceful curve. Without these physical guides, the Parthenon's famous columns would have been a chaotic collection of individual interpretations, ruining the harmonious visual rhythm that defines classical architecture. This was the ancient world's version of mass production. templates turned artistic vision into a scalable, efficient process, ensuring that beauty itself could be standardized. This principle of modularity extended beyond decoration to the very bones of a building. Standardized stone blocks, shaped with the help of set squares and templates, could be quarried miles away and still fit together perfectly upon arrival, like a colossal, preordained puzzle. This systematic approach reveals a sophisticated understanding of project management, where consistency was not left to chance but was engineered into every step, from the grand plan to the smallest decorative detail. While the Gromer mastered the straight line and the Corobates the long grade, some of the most breathtaking ancient structures demanded a mastery of the angle itself. This need gave rise to the Dioptera, an instrument of astonishing versatility. At its heart, it was a circular plate, carefully engraved with degree markings upon which a sighting tube could pivot. This simple yet profound design allowed a surveyor to do something previously impossible: measure any angle in the landscape, both horizontally and vertically, with scientific precision. Imagine a Greek engineer tasked with carving a theater into a hillside. Each row of seats needed to offer a clear view of the stage, requiring a complex, curving layout of precise, graduated angles. The Dioptera made this possible. By setting up the instrument and sighting along its tube, the engineer could mark out the fan-like segments of the seating, ensuring that every citizen had an unobstructed line of sight. This was a leap from the rigid 90-degree world of the Gromer into a realm of fluid, calculated geometry. The Dioptera's capabilities extended far beyond civic projects. It was likely the key to one of the most daring engineering feats of the ancient world, tunneling from both ends of a mountain to meet in the middle. Surveyors would have used the Dioptera to establish the precise direction and slope for each tunnel heading, their calculations converging deep within the earth with breathtaking accuracy. This tool even turned its sight to the heavens and the earth's grandest features, allowing for the measurement of a mountain's height or the distance to a far-off ship. This was not just alignment, it was true metrology, the science of measurement. The Dioptera gave builders the mathematical confidence to move beyond simple squares and right angles, embracing the complex forms that would define the architectural splendors of the Hellenistic age and beyond. A rope pulled taut across an empty field was the first line ever drawn by an architect. In a world without steel tapes, specially prepared cords, soaked in oil or resin to resist stretching, became the primary means for transferring massive dimensions from a plan to the earth itself. A master builder would arrive at a site with a collection of these standardized ropes, perhaps each exactly 100 cubits long. With a team of assistants, he would stretch the first cord to define the building's primary axis, a physical act that transformed a theoretical line into a tangible reality. The tension in the fiber created a perfectly straight reference over incredible distances, a principle we still use today with chalk lines, but these ropes were far more than simple distance markers. A knotted cord could function as an ancient calculator. By using knots to mark specific intervals, a builder could quickly lay out a grid on the ground, calculating areas for floors or volumes for earthworks without any written arithmetic. This was mathematics made physical, a tool that turned complex calculations into a series of simple, repeatable actions anyone could perform. The symbolic weight of this act was immense. In many ancient societies, the ceremony of stretching the first cord was a sacred rite, often performed by a priest-king. It was seen as an act of cosmic order, imposing the geometry of the human will upon the formless chaos of the natural world. The humble rope, therefore, existed in two realms simultaneously. It was the gritty, practical tool that laid the foundation for a palace, its fibers gritty with dust. And it was a profound symbol of creation itself, a line drawn between the idea and the monument, between chaos and the enduring human desire for precision and meaning. This natural law of water was a tool as reliable as any metal instrument. A simple length of hollow reed or a pair of connected basins could create a perfect level line that snaked around corners and across impossible distances. The principle was beautifully straightforward. If you fill a tube with water, the surface at both ends will always settle at exactly the same height, regardless of the ground in between. Imagine a team working on the long, flat track of a Roman circus. An overseer could stand at one end with a basin of water, while an assistant walked hundreds of feet away with a second connected vessel. By watching the water's surface, they could mark 2 points that shared the exact same elevation, even if a small hill stood directly between them. This method was immune to the errors that could plague a long, rigid level, which might sag or be thrown off by a single unsteady stone. It allowed for the creation of a continuous, unbroken plane of reference across the entire vast length of the racecourse. This same technique, on a truly monumental scale, is believed to have been used to level the Great Pyramid's 13-acre foundation. Workers likely dug a grid of shallow trenches across the entire bedrock site and filled them with water. The still surface created a single, perfect horizontal plane against which every inch of the foundation could be checked and painstakingly trimmed. By observing nature's unwavering constant, these builders solved one of the most fundamental challenges of large-scale construction. How do you ensure that 2 points you cannot even see from one another are perfectly level? The water level provided the answer, a tool that was both humble and profoundly intelligent, turning a simple observation of the physical world into the very bedrock of architectural precision. The polished granite cubit rod and the bronze set square did not appear from nothing. Their origins stretch back into a much deeper past, to a time when humanity first began to impose geometric order on the world. Over 11,000 years ago, at a site in modern Turkey known as Göbekli Tepe, communities were already assembling monumental stone circles. These were not simple huts. They were complexes of massive, T-shaped limestone pillars, many weighing over 10 tons, arranged in precise oval and circular patterns. The sheer scale and clear intentionality of these structures pose a profound question. How could hunter-gatherers without metal, without the wheel, and without writing achieve such coordinated construction? The answer lies in the world's first, most fundamental drafting kit. Imagine a long, straight wooden pole, stripped of bark and hardened in a fire, planted firmly in the earth. This simple sighting stake became the fixed point from which all other lines could radiate. By connecting these stakes with cords made of sinew or plant fiber, the builders could map out the diameters and circumferences of their sacred enclosures. The geometric harmony found at Göbekli Tepe, with pillars spaced at regular intervals, suggests they used these knotted ropes not just for measuring, but for creating basic geometric shapes, likely discovering the principles of the circle and the radius through physical practice. These were the prototypes, the ancestors of the plumb line and the Gromer. The meticulously carved reliefs of animals on the pillars themselves offer another clue. The consistency in the depth and style of these carvings across different stones implies the use of a template, perhaps a master pattern carved on a piece of wood or soft stone, allowing multiple artisans to replicate the SAME Chinese letter with remarkable fidelity. This was not yet formal engineering, but it was the undeniable seed of it, the drive to plan, to measure, and to execute a shared vision on a colossal scale was already fully awake. This nascent understanding of space and form, born from stakes and cord in the dawn of civilization, laid the essential conceptual groundwork. It proved that the impulse to translate a grand design from the mind into enduring stone is a fundamental part of the human story, a legacy that would be refined over millennia into the tools that built the world's wonders. The stone circle was not merely an enclosure, it was a clockwork of the heavens. This profound connection between the stars and the earth defined the very soul of ancient architecture. For civilizations like the Egyptians, building a temple was an act of cosmic alignment, a way to anchor their world to the eternal rhythms of the universe. To achieve this, the tools of the astronomer and the architect were one and the same. The Merkhet, a simple notched palm rib, became their most sophisticated instrument for capturing true north. An astronomer would set up two of these devices, aligning the slit in each with a plumb line hanging behind it to ensure a perfectly vertical sight. He would then patiently wait for a specific circumpolar star, one that never sets, to cross the meridian, the imaginary north-south line in the sky. At the precise moment the star appeared in the slit of one Merkhet and disappeared in the slit of the other, he had his reference. A line drawn on the ground between the two instruments became a near-perfect north-south axis. This was not a rough approximation. It was a line drawn from the stars themselves, a celestial blueprint transferred directly to the sand. The Great Pyramid's staggering alignment, its sides deviating from true north by less than 1/10 of a degree, stands as a silent witness to the power of this method. But why go to such extraordinary lengths? This was far more than a technical exercise. It was a philosophical and religious imperative. By orienting a pyramid or a temple to the cardinal points, the builders were weaving it into the cosmic order. The structure became a microcosm, a model of the universe where the earthly and the divine met. The sun would rise and set along its designated faces at the solstices. The stars would circle directly above its apex. Every stone was placed in conscious harmony with the cosmos. This holistic vision meant that the first step in drafting a sacred building was not to draw its walls, but to chart the stars. The precision we marvel at today was not an end in itself, but a means to a spiritual one, a testament to a world where science, faith, and stone were inseparable. That precise celestial alignment and the perfect curve of an arch all relied on a silent, unseen foundation. Behind every physical tool, from the stretched rope to the bronze template, was the relentless engine of calculation. The abacus, with its beads sliding on rods, was the physical embodiment of this intellectual power. Though not a tool that touched stone, it was indispensable for translating visionary designs into buildable realities. Consider the challenge of the Parthenon. Its breathtaking harmony is not an accident of aesthetics, but the product of deliberate mathematical principles like the golden ratio. To achieve this, architects had to calculate complex proportions, ensuring that every column, every space between them, related to the whole in a precise, mathematically beautiful way. This was not simple addition or subtraction. It was advanced geometry made practical. The abacus allowed a master planner to work out these intricate relationships, turning an abstract ratio into a set of specific, measurable dimensions that could be communicated to the teams on the Acropolis. The need for calculation went far beyond beauty. How much stone was needed for a pyramid's next course? What was the exact angle of incline for a ramp that could lift blocks weighing tons? These were not questions answered by guesswork. They were complex problems of volume, trigonometry, and structural load that required reliable computation. The abacus provided the speed and accuracy for these essential tasks, transforming mathematical theory into actionable numbers. This computational capability marked the fundamental difference between a builder and an architect. A builder follows instructions, but an architect creates them through foresight. With the abacus, a designer could predict the outcome of a design, calculating stresses and strains before committing to a single, irreversible action. He could plan the entire sequence of construction, anticipating problems and ensuring that the thousands of individual components, shaped by countless hands with simpler tools, would all converge into a single, coherent, and stable form. In the end, the most crucial instrument was the human mind itself, and the Abacus was its essential partner, directing the entire orchestra of physical tools toward a perfect, predetermined conclusion. A rope stretched between two stakes could now reveal the height of a distant pyramid. This was the profound power of Greek geometry in action, turning abstract theorems into tangible tools for the builder. Before this intellectual revolution, architectural knowledge was largely passed down through tradition and practical trial and error. A technique worked because it had always worked. But Greek thinkers like Euclid and Pythagoras unlocked the underlying reasons why these methods were successful, providing a universal and provable foundation for construction. They demonstrated that the principles governing a perfect triangle drawn in sand were the very same principles that governed the stability of a massive stone structure. This was a monumental shift from empirical craft to engineering science. Suddenly, a builder was not just following a set of instructions, he was applying a fundamental law of the universe. The simple knowledge that a triangle's internal angles always add up to 180 degrees became a powerful tool for measurement. If a surveyor needed to find the height of a cliff to plan a bridge, he could use a simple device called a Dioptera to measure the angle from a known distance. By creating a small, right-angled triangle with his instruments, he could then use the properties of similar triangles to calculate the immense height he could not physically reach. The large, real-world triangles shared the exact same proportions as the small, measured one. The theorem gave him absolute confidence in a result he could not verify any other way. This new understanding did not immediately replace the trusted Plumbob or the set square. Instead, it infused these tools with a deeper meaning and expanded their potential. A knotted rope was no longer just a device for making a right angle. It was a physical representation of the Pythagorean theorem, a portable piece of mathematical truth. This synthesis of mind and hand elevated the entire practice of design. An architect could now innovate with greater boldness, confident that his complex visions were supported by irrefutable logic, not just hopeful tradition. The legacy of this Greek synthesis is the very concept of architectural theory itself, a bridge of pure reason that connects a brilliant idea on parchment to its magnificent realization in stone. Yet the same rationality that mastered the straight line and the arch also yearned for a touch of grace. High atop the slender columns of an Ionic temple, the stone seems to curl into a perfect, frozen spiral. These elegant scrolls, known as volutes, presented a paradox. How do you standardize a form that is fundamentally a continuous, flowing curve? The solution was a masterpiece of applied geometry. Architects did not leave this delicate shape to the freehand skill of a carver. Instead, they constructed the spiral using a series of carefully plotted circles. The evidence points to a process where a master designer would first lay out a grid of guiding lines on a flat surface. Within this grid, a series of small circles would be drawn using a compass, each one sharing a common tangent point. The outer arc of each successive circle, when connected, formed the seamless, expanding curve of the volute. This geometric construction transformed an artistic flourish into a repeatable mathematical sequence. Once perfected, this master drawing was used to create a durable template, probably from sheet bronze or a hardened wood. This template was the key to consistency. On a bustling construction site, a craftsman could place this guide against the rough stone capital and trace the complex spiral profile with a sharp stylus. Suddenly, the most intricate element of the design was reduced to a simple, foolproof task. This meant that every single Ionic column in a long colonnade, whether in a temple in Greece or a library in Rome, could bear an identical volute. The visual rhythm of the entire structure depended on this exact replication. The successful spread of the Ionic order across the ancient world is a testament to more than just aesthetic taste. It is proof of a powerful and portable system of design, where even the most beautiful curves were not left to chance, but were governed by the unwavering logic of the compass and the line. The Pantheon's dome floats in space, a perfect hemisphere of Roman concrete that has defied gravity for nearly 2,000 years. This breathtaking achievement was not born from the stone itself, but from an act of incredible foresight, a masterpiece of wood that existed only long enough to give the concrete its eternal form. Before a single bucket of mortar was mixed, Roman engineers constructed a colossal temporary skeleton, a wooden formwork that was, in essence, the final building made in a perishable material. The design and assembly of this centering required a level of drafting skill equal to the architectural plans themselves. Every curve of the dome, its precise spherical geometry, and the exact placement of the 5 concentric rings of coffers were first laid out and built into this intricate wooden scaffold. This was not a rough support, it was a full-scale, 3-dimensional blueprint, a negative space carved from timber that would define the positive space of the dome. The construction of this temporary wooden mountain was a feat of engineering in its own right. Carpenters had to calculate and cut thousands of wooden members to exact angles and lengths, ensuring the entire structure could bear the immense wet weight of the concrete without sagging or shifting. The varying thickness of the dome, which grows thinner and lighter toward the summit, was precisely mirrored in the formwork's design. Each coffer, those elegant recessed squares that patterned the ceiling, was created by a wooden box built into the formwork, a void that became a permanent feature of lightness and shadow. The Pantheon, therefore, stands as a permanent monument to a temporary wonder. It is the ultimate testament to an ancient truth that the most enduring structures often rely on the most precise and carefully considered temporary works, a perfect draft written in wood that was erased by the very stone it was created to hold. That grand Roman tradition of precision did not simply fade away, it was abruptly interrupted. The systematic knowledge of tools like the Dioptera and the Corobates, which had allowed engineers to plot aqueducts and tunnel through mountains, fractured and was largely lost across Western Europe. In its place arose a different kind of genius, one born from practical necessity rather than preserved theory. The master masons who conceived the great Gothic cathedrals were brilliant empiricists. They worked with plumbobs and levels, but their most telling tool was the tracing floor, a vast flat surface of plaster or stone, often within the cathedral workshop itself. Here they would scratch out their designs at full 1:1 scale. A complex window tracery or the intricate profile of an arch was not drawn on a small parchment, but laid out life-size on the floor. This was architecture by direct physical translation, a return to a hands-on process where the plan and the final product were one and the same. It was an incredible feat of spatial reasoning, but also a fragile method. The knowledge was locked in the minds and practiced hands of the masons, passed down through guilds as closely guarded secrets, not recorded in universally accessible texts. Yet even as this empirical approach reached its zenith, a parallel stream of classical knowledge had been flowing, preserved and enhanced within the Islamic world. Scholars in Baghdad and Cordoba had not only safeguarded Greek and Roman texts on geometry and engineering, they had expanded upon them, refining tools like the Astrolabe for both astronomy and surveying. The reconnection of these two worlds through trade and the intellectual fervor of the Renaissance sparked a revolution. Classical texts, translated from Arabic into Latin, began to circulate once more in the West. Architects like Filippo Brunelleschi, who would famously crown the Florence Cathedral with its immense dome, were voracious students of this rediscovered knowledge. He combined the mason's practical understanding of materials with the recovered Roman principles of structural engineering and precise measurement. This cycle of loss and rediscovery is a profound lesson in the fragility of technology. It underscores that the ancient toolmakers were not just skilled craftsmen, but sophisticated scientists whose innovations were so advanced that it would take centuries for the world to fully recover their genius and begin building upon it once again. A building's dialogue with the cosmos required more than just a straight line to the North Star. The Astrolabe, an intricate brass disc etched with a map of the heavens, was primarily a navigator's guide and an astronomer's clock. Yet in the hands of a master builder, its precise scales and sighting vanes became a source of critical environmental intelligence. Before a single line was drawn on a drafting board, this instrument could answer fundamental questions about the site itself. By measuring the angle of the sun at its zenith or the height of the pole star above the horizon, a surveyor could determine the exact latitude of the building's location. This was not trivial information. In the design of a great library or a royal audience hall, architects used this data to calculate the sun's path across the sky for every day of the year. They could then strategically position windows and design shading colonnades to capture the low, warming light of winter while deflecting the high, harsh glare of summer. This was passive solar design mastered centuries before the term existed, all guided by the celestial data captured on the astrolabe's delicate rete. Its ability to function as a precise timekeeper also shaped architectural experience. The positioning of a specific window or a carefully angled light shaft could be planned so that a beam of sunlight would illuminate a sacred statue or mark a significant date on the floor, turning the building itself into a monumental calendar. The astrolabe itself never touched a stone, but the knowledge it provided was etched into the very soul of the design. It represents a crucial but often invisible layer of the drafting process, where understanding the world was the essential first step toward reshaping it. This sophisticated tool reminds us that the most enduring structures are not just precisely built, they are precisely situated, harmonizing with the unyielding rhythms of the sun and the stars. That master's eye, calibrated by years of experience, was the final instrument in the toolkit. In an age before formal engineering schools, the profound knowledge of how to use a plumbob or a set square was not written down in manuals. It was breathed into the next generation through the intimate, demanding relationship of apprenticeship. A young student would spend years at his master's side, not just watching but doing. He would learn the exact feel of a perfectly balanced plumb line, the subtle sound a chisel makes when it strikes a true surface, and the way shadows can reveal the slightest deviation from level. This was a complete education of the hand, the eye, and the mind. The master imparted more than technique. He passed down the accumulated wisdom of generations, the tricks of the trade that turned a good builder into a great one. He taught the standard proportions that made a column look both powerful and graceful, and the critical judgment of when a stone, though nearly perfect, had a hidden flaw and should be rejected. This oral tradition was the living library of ancient engineering. It ensured that the sacred geometry and precise methods were preserved and passed on with fidelity. Yet this system, for all its strength, was also incredibly fragile. The deepest mysteries of the craft were closely guarded secrets, the exclusive property of the master and his chosen successors. If a lineage was broken by conflict or illness, if a workshop was dispersed, that hard-won knowledge could vanish in a single generation. The true power of the tools, therefore, did not reside in the bronze or the wood itself, but in the skilled hand that held them and the trained mind that guided them. It was this human element, this fusion of inherited wisdom with practical skill, that ultimately animated the simple tools, transforming abstract lines on a plan into the enduring stone wonders we still marvel at today. A granite cubit rod did not simply measure distance, it conquered time. The multi-decade construction of a pyramid demanded tools that were as enduring as the monument itself. A wooden set square, exposed to sun and rain on the Giza Plateau, would warp in a single season, its perfect right angle slowly twisting into uselessness. But a square cast from bronze possessed a near-permanent memory of its form. This was the silent revolution of metallurgy, transforming drafting from an art of constant recalibration into a science of reliable constants. The development of hardened copper and later bronze and iron allowed for the creation of tools that could be passed from a master to his apprentice and then to the next generation without any loss of fidelity. This material permanence was the bedrock of architectural ambition. A pharaoh could commission a temple knowing that the standard of measurement used on its foundation would be identical to the one used on its capstone 50 years later. The choice of material was a direct investment in precision. A hardwood level might serve for a small house, but only a sturdy, metal-reinforced Corobates could maintain its truth over the 20-foot spans needed to chart an aqueduct's course. The very resistance of bronze to the wear of daily use meant that the marks engraved upon it, the critical divisions of the digit and the palm, remained sharp and unambiguous. This parallel evolution of smithing and drafting is a story often told in stone but forged in metal. The soaring heights of Gothic spires and the vast spans of Roman arches were not just triumphs of design, they were ultimately made possible by the unyielding integrity of the iron compass that plotted their curves and the bronze template that guided their carving. The quest for architectural precision was never confined to one continent. Across the vast expanse of the Pacific, in the high Andes of South America, the Inca civilization achieved a stonework so precise it defies modern explanation. Their massive structures, like the fortress of Sacsayhuaman, were built with enormous, irregularly shaped blocks of stone that fit together without a trace of mortar. The joints between these stones are so tight that not even a razor blade can slip between them. They achieved this not with complex metal tools, but with an intimate knowledge of their materials. Using hard stone hammers and bronze crowbars, craftsmen would patiently peck and abrade the surfaces, test fitting one block against another repeatedly until the contact was perfect. While we have not found their equivalent of a formal blueprint, the sheer perfection of the final product speaks to a profound process of mental drafting, a three-dimensional puzzle planned and executed with unwavering discipline. The absence of a written language does not mean an absence of design. It suggests a system of measurement and proportion so deeply ingrained in the craftsman that it was communicated through action and result. On the other side of the world, ancient Chinese engineers operated with a different kind of systematic rigor. For the construction of the Great Wall and other massive public works, they employed sophisticated bronze calipers and standardized official measures. These tools ensured that the millions of bricks and stones produced across a vast empire would conform to a single, unvarying standard, allowing for seamless assembly by different work crews over centuries. This parallel development from the Andes to Asia reveals something fundamental about our shared human story. It was not a single culture that gifted the world with precision engineering, but a universal human impulse. Different environments and different challenges prompted the independent invention of tools and techniques, yet all were united by the same driving ambition to impose order, stability, and beauty upon the world through measured, deliberate design. A single tool is a note, but their combination is a symphony. The real magic of ancient construction was found in the seamless choreography of these simple instruments, a process that turned a chaotic quarry of stone and ambition into a controlled, precise assembly line. Imagine the sequence on the first day of a new temple. Before any stone was cut, an astronomer would use the Merkhet to draw a line from the stars onto the earth, establishing a sacred north-south axis. This celestial starting point was then handed off to the surveyor and his Gromer, who used its hanging plumb lines to project that orientation into a vast grid of perfect right angles across the landscape, mapping the entire foundation. Next came the water level, its still surface creating an unbroken horizontal plane against which the site's bedrock was painstakingly trimmed to perfect flatness. With a grand layout set, the work of raising the walls began. Thousands of masons, each with their own set square and plumbob, ensured every block was true, checking each stone's angles and faces against these constant guides. And for the final layer of beauty and consistency, bronze templates were pressed against rough stone, transferring intricate carvings and profiles with flawless repetition. This was not a collection of random tasks. It was a deeply integrated system, a cascade of precision where each tool verified the work of the one before it. The plumb line confirmed the Gromer's alignment, the set square ensured the template would sit flush, and the water level guaranteed the whole structure rose from a perfectly stable base. This orchestration of simple technologies allowed a single, grand vision to be fractured into millions of individual, manageable tasks, all converging with breathtaking accuracy. The lesson for us today is profound. Their greatest innovation was not the Cubit rod or the Dioptera, but the underlying process itself. It demonstrates that systemic thinking, the careful integration of reliable steps, is what truly enables human ambition to take permanent, magnificent form. From the knotted ropes of the Egyptians to the bronze squares of the Romans, these ancient drafting tools were masterpieces of elegant simplicity. They demonstrate a profound truth that precision is not born solely from complex technology, but from a deep understanding of natural principles and a commitment to meticulous process. Each tool was an extension of the architect's mind, a physical key that unlocked the ability to translate a grand, visionary idea into the enduring language of stone and mortar with an accuracy that still leaves us in awe. The legacy of these instruments stretches far beyond the ruins we admire. It lives on in the very DNA of modern engineering, in the fundamental principles of standardized measurement, of alignment to the world, and of careful, step-by-step planning that governs every skyscraper and bridge we build today. Gazing upon these ancient marvels, we are connected to a timeless human endeavor, the relentless pursuit of perfection through measured thought and skilled hands. If this journey into the roots of architectural precision resonated with you, we would be honored if you subscribed for more explorations into the world's great historical mysteries. And we are truly curious, which of these ancient tools do you believe was the most crucial? Let us know your thoughts in the comments below.